Hi, in this video I'm going to talk about the practical meaning of vectors and matrices. Now you can talk about the mathematical behavior of vectors and matrices, but what I want to talk about is really how they relate to real life situations and why they're so useful in modeling systems. First, let me start with a vector. I can define a vector as a list of numbers which is considered as a single data item. For example, rows of a spreadsheet. So these numbers may represent values of related variables that characterize the state of a system. So some examples. You can have a vector of prices. For the current prices at the supermarket. You might list these in a spreadsheet. You might list columns, be bread, milk, and eggs. Right? And you'd put all the prices in one row. So these prices are in some way related, and I can consider them as a single data item. So typically you'll represent them. So if the bread price, let me make that a little bit thinner. That's kind of thick. It's not so good. Bread price is equal to, so let's start again here. Okay, so if the bread price, let's say it's 94 cents. Okay, and if the milk price is $2 or $2.12, and then eggs price, let's say it's 89 cents, okay, then you could have a vector 0.94, 0.2, 2.12, and 0.89. Okay, and then of course you need to know that this first component relates to bread, this second component relates to milk, this third component relates to eggs. So the order certainly matters in a vector. Now, here I'm representing the numbers as a row. Sometimes people were represented as a column. So for our purposes, these two are equivalent. Okay, so that's a vector. Vector of locations. This is from physics. This is actually the original motivation for vectors. You have 3 dimensions. You have 2 flat dimensions and 1 vertical dimension. So you can characterize the location of an object in space with 3 numbers, and those 3 numbers are considered the 3 components of a 3-dimensional vector. Now, if you throw time into the mix, that's a 4th dimension. We don't really care about the first 3 are space dimensions, and the 3rd is a time dimension. All we care about is we have 4 numbers that are related as a single item, and they go together. Another place where vectors come into play are vectors of probabilities. Okay. For instance, if you have a patient and their current prognosis is good, fair, or poor, right? You could say that currently their prognosis have a 50% chance of a good prognosis, and then a 20% chance of a fair prognosis, and a 30% chance of a poor prognosis. Then that patient's prognosis, that patient's current health state, would be characterized by this vector of probabilities. Now, when you have a vector of probabilities, they have to sum to 1. So hopefully I've given you an idea that vectors can describe a variety of situations, and the numbers in a vector can describe a variety of things. Here we have prices, here we have locations, here we have probabilities, and there are other options as well. All right. Now, so that's a vector. So what's a matrix? A matrix is a table of numbers that expresses interrelationships between the components of 2 vectors. All right. Now, here first you have table. Right. Here you have a row of numbers. A matrix is a table of numbers. Right? Now, you could think of any table as a matrix, but specifically in mathematics, when we're using them mathematically, table expresses interrelationships between the components of 2 vectors. And I'll give you some examples below. So matrices are often used to describe systems that have a linear relationship between inputs and outputs. So the input would be one vector, and the outputs would correspond the other vector. Okay? So let's look at some examples. If you look at shopping costs for different shoppers, okay? So you'd have different amounts of bread, eggs, and milk, and suppose you have 3 different shoppers. So let's see, there's for Mary, say Joseph is another shopper, and Dana, okay? So you've had bread, eggs, and milk cost for Mary, Joseph, and Dana. Okay, so in this case, Mary and Joseph and Dana may have different costs because they buy different amounts of bread, different amounts of eggs, different amounts of milk. All right. Now, another example is rotation of an object in space. Okay. So location X, Y, Z. So for instance, if I have a cube in space, and I take one particular location on that cube, if I take this corner and I rotate the cube, right, then the location of this point moves to another point. Now, the location of the new point depends on the location of the original point, right? If this one was X, Y, Z here, then this would go to another point, X prime, Y prime, Z prime, if I rotate this cube in this direction. But this point here would go to another point down here. So if I call this point, let's just call this UVW, this would go to U prime, V prime, W prime. Okay. So here I have my initial vector, my initial location goes to a final location. And there's a relationship, there's actually a linear relationship between the initial location and the final location. And this can be expressed by a matrix. Changing probabilities is another example of a matrix. Suppose someone has a treatment. Okay. The treatment will change the prognosis. Okay. And let me show you down below how a linear relationship can express all three of these situations. Okay. First of all, let's consider the shopping cost case. Okay. Now, here we have A, B, and C. In this case, A, B, and C would be prices. Okay. And then these are my three shoppers. Okay. So I said Mary, Joseph, and Dana. So this would be Mary, this would be Joseph, and this would be Dana. Okay. And over here, instead of A, B, and C, I would have bread, milk, and eggs. Okay. All right, so you see these numbers labeling these different lines here. This 10 represents the fact that Mary buys 10 units of bread. Mary also buys 3 units of milk, and Mary buys 6 units of eggs. You see? So the number here labels the edge. Okay. So if I take Mary, so she buys 10 bread. She also buys 3 milk. And she also buys 6 eggs. Okay. Joseph, on the other hand, if you look at the ones for him, I'll use a different color for Joseph. Joseph would be what? Let's see. Joseph buys 5 units of bread, this one here, and then 12 units of milk and 9 units of eggs. So Joseph would be 5 bread plus 12 milk plus 9 eggs. And then finally we have Dana. Dana, we'll use orange for Dana here. Dana buys 25 bread, 20 milk, and 3 eggs. So we have 25 bread plus 20 milk plus 3 eggs. Okay. Now, how do these numbers relate to a matrix? So I said matrix relates inputs to outputs. So I'm going to list the inputs on the top, and I'll list the outputs on the side. Okay. Now my inputs were bread, milk, and eggs. My outputs were Mary, Joseph, and Dana. Okay. Of course, this M here is not the same as this M here. I'm just using a shorthand to label the rows and the columns, right? So my inputs relate to the columns, my outputs relate to the rows. Okay, so I have 9 numbers in this matrix. So what are the 9 numbers? Okay. So Mary buys bread. Mary buys 10 units of bread, okay? Buys 3 units of milk and 6 units of eggs, okay? Joseph buys 5 units of bread, 12 units of milk, 9 units of eggs. Sorry, I put E here. That should be a 6. Okay, last one here, 25, 20, and 3. All right. So there's my matrix. Okay. So you can see that these numbers completely characterize the relationships between my outputs and my inputs. And in fact, the way that this would be notated in mathematics is I would write this matrix here. So let me call this matrix capital A. Okay. So I would write this number is as the output vector is equal to the matrix A times the input vector. And in this case, we would write the vectors as columns. Okay. And this would also be a column. Okay. So if I want to be more specific about that, my output vector, here I have the amount that Mary buys, amount that Joseph buys, amount that Dana buys, and that's going to be equal to, I don't want to rewrite this vector. Well, actually, I could just grab this because I have this handy dandy here. I'll just grab this matrix here and copy it and paste it here. And I'll shrink it so it fits. Okay, so I have this, and it's that matrix times my input, which would be the eggs, the bread, milk, and eggs. Okay, all right. Now for the bread, milk, and eggs, I would put this would be the inputs are the prices, and then these would be the costs. All right. So linear relationship between the inputs, which in this case are the prices, and the costs, which are the total purchases of the three shoppers. Okay. So this diagram here well represents this multiplication process, right? This 10, 3, 6, that represents the fact that the three lines into Mary, that's 10, that's 3, that's 6. Okay. So you can read this relationship off by the lines that are going into Mary. You can read this relationship off by the lines that are going into Joseph, this one by the lines that are going into Dana. Right? And this is a very useful representation. And in the next video, we'll see how we can use this representation to understand matrix multiplication. And I'm going to introduce a couple of concepts that you may or may not be familiar with, inner and outer products, and show how you can analyze this process of matrix multiplication through inner and outer products. Okay, thanks for listening. See you in the next video.